Today we're going to talk about rate of change, and it's actually something that you talked about in the past. You have to think back to grade 9, because in grade 9 you did a lot of stuff with rate of change, although they may not have called it that. They may have called it slope. Now in grade 9 we dealt specifically with linear functions. And if you think about a line and you calculate the slope of that line, remember it didn't matter which 2 points you picked, you're going to get the same answer, because on a line or a linear function the slope is a constant. Now we're not doing much with lines at all in this unit, but let's just remind ourselves what we did when it was a nice question. If you're going to calculate slope, we had a couple of options. We could call it slope, first of all, or we could call it m. I have no idea why they came up with that. In words, we could do slope as rise over run, and that reminded you that the rise went with the y value, so it was y2 minus y1 over x2 minus x1. But sometimes in science, they did it this way, delta y over delta x, or the change in y values or the change in x, rate of change. So there's a lot of different ways to talk about it, and we're going to pick some of those favorites as we deal with the nonlinear functions. Because with those, parabola, cubic, quartic, any of those, slope is not constant. And it really changes from one interval to the next. And even if we just look at this basic parabola off to the right, we should be able to see that. So what we do is we pick 2 points on the curve, and that creates an interval. And we use those 2 points to calculate what we call an average rate of change for that section of the curve. For example, if I put a line through this guy here, so I'm connecting this point to this point, I can calculate the slope on that interval. It looks like I'm going from x values of 2 to about 4.5 or something like that. And I'll get a representation of what's happening. Remember, a line that looks like this, a line that goes up left to right, would have a positive slope. And on that section of the curve, this function is increasing. Remember the first unit that we did in this course? Whereas if I picked a section over here, I'm just going to freehand this one, and did this slope calculation, I would be getting a negative slope, and that section of the curve is decreasing. So that makes sense. But as soon as you get into curves, you have to be careful, because I could pick these 2 points and calculate the slope, and what would it tell me about the function? Not much at all. Because as soon as you cross a turning point, sometimes those slopes that you're calculating don't have much meaning. So it's really important to keep points that are on one side or the other of a turning point, which you won't know if you're not familiar with the curve, and so we have to watch that when we set up the questions. Thing to be aware of, those lines that I've drawn, and yes, some of them are freehand, but you get the idea. That's something that's called a secant. So a line that connects any 2 points on a curve is called a secant. So we have 3 of them drawn there. I think the black and the blue secants are useful to us. The green secant, not going to tell us so much about what's going on. But we can use that then to calculate the average rate of change, using the slope of the secant to approximate what's going on in that section. If we think about the formula then, well, we're calculating an average rate of change, which we sometimes refer to as the slope of the, and then as a subscript secant. I don't really love that notation, but it can be there. It's still the same calculation. We're using 2 points and calculating rise over run, which is, you know, the curve doesn't follow the line because it's a curve. But it's still the same calculation of rise over run, y's over x's. So the thing is now, because we're doing more in advanced functions, we want to use function notation. So we're going to say that it's the change in the function compared to the change in the x values. Because remember, the x values create the function values or the y values. So really, what we've got is the function at one point minus the function at the other point. Those are the 2 y values compared to the change in the x values. And we're going to be using that version of the formula, f of x2 minus f of x1 over x2 minus x1, more often than not. But it really is just a stepped up version of y2 minus y1 over x2 minus x1. So let's work through a couple of examples. I need some more space. Because we know we're dealing with a curve, x squared, I can't just say, what's the slope of x squared? We tried with step pattern in grade 10 to describe what was happening, but that was very specific to parabolas. Would a step pattern work with a cubic or a quartic? And it's not going to. So we use slopes of a secant, average rate of change, to approximate what's happening on an interval. So if I want to know what's happening for a basic parabola on the interval from 2 to 5 inclusive, what I'm looking for there is an average rate of change. Okay, we're going in green. So it's f of 5 minus f of 2 over 5 minus 2. There's my first x value, there's my second x value, and I'm substituting into the green box up on top. And then we basically just start doing some math. I'm substituting into f of x, which is equal to x squared, so f of 5 would be 25, f of 2 would be 4, 5 take away 2 is 3, 25 take away 4 is 21, divided by 3 is 7. And so the average rate of change on that interval is 7. I would rise 7 and run 1, rise 7 and run 1, and kind of simulate what's going on. As soon as we put in negative x values, you tend to stress out. There's x1 and there's x2. And so if I want the average rate of change, it's f of -1 minus f of -3 all over, careful, -1 subtracts -3. Fun times. What do we got going on? F of -1, so I'm squaring it, so that's 1. I'm subtracting 9. -1 subtract -3 is positive 2. 1 take away 9 is -8, divided by 2 is -4. Don't get hung up on too much which point is which. Remember when we talked about slope, you always said which point goes first. It didn't matter as long as you were consistent. If for some unknown reason you felt like making this one your x1 and this one your x2, well, then our average rate of change would be f of -3 minus f of -1 over -3 subtract -1. And on the bottom, then we get -3 plus 1, or -2. But the top is 9, take away 1. So we still have, the same number as negatives in there. It's 8 divided by -2, still -4. So you get the same answer either way, but we commonly call the first one an interval x1 and the second one x2, but it really doesn't matter. Also remember what this one's telling us, a slope of -4, an average rate of change of -4. In this section of the graph, we're going down, we're decreasing, down 4, 1 to the right, down 4, 1 to the right, approximates what's happening in this section of the graph. And if you think about a parabola, you know what it looks like. And a parabola from -3 to -1, that's coming down towards the vertex at 0, 0, this basic parabola. Okay, so that's one with a very simple function to deal with. And of course, we're going to challenge you a bit more. So here's just another more entertaining parabola, x squared plus 3x minus 4. And again, finding the average rate of change over each interval. So we want an average rate of change, weird r, which will be f of -3 minus f of -5 all over -3 subtract -5. So the bottom is fairly straightforward, doing some integer work there and getting an answer of 2. On the top, though, the substitution isn't quite as easy. So you have to decide how you want to show that. I don't want just an answer to magically appear, but perhaps we might kind of substitute and do a bit of the math on our own. If I put a -3 in there, squared is 9, times +3 is -9 minus 4, and then I'm subtracting, need a bit more room here. Put in a -5, that's 25, multiply by +3 is -15, and then I subtract 4. So I'm simplifying there and getting -4, subtract 6 over 2, and that comes out at a -5. Okay, so don't just magically appear your way to the answer. Show a little bit of work. Some people will off to the side calculate f of -3, calculate f of -5, and then put those numbers in. So find something that makes you comfortable and work through it that way. So maybe I'll do that for the next one just to show you what I mean by that. This would be f of 6 minus f of 2 over 6 minus 2. So that's pretty nice, but there's some work going on the top. So maybe we're going to say that f of 6 is equal to 36 plus 18 minus 4, and that's not a number I can think of quickly, 50. So that's going in this location. Then I'm subtracting f of 2, which is going to be 4 plus 6 minus 4, which is 6, and then putting the answer in. So if that's how you like to manage it a little bit better, I'm cool with that. So it's going to be 44 divided by 4. That's messy, which is 11. Okay? So you decide how you show that when there's a bit more action involved in the function. Last example puts it into an application. Because look at this equation, or this function. P of d equals 100 times 1.06 to the d. Potentially, and I don't know, because there's no story with this one, but potentially P is for population, and D is for days. And if that were true, we're going to find out something about this population growth over a number of days. Remember, P is the population, in place of the Y values goes on the top. D is the days, in place of the X values goes on the bottom. So we could get a growth of maybe people per day if that's what this was measuring. And again, that makes a bit more sense, rate of change, rather than just a slope of like -5 or a slope of 11. So process is the same. We're finding an average rate of change. Population 5 minus population 0 over 5 minus 0. And here I would be grabbing a calculator and just putting in the final answer. I did this beforehand, so I would know what I was doing, 133.86, and that just keeps on going. The population of 0 is 100, so you can be exact and subtract 100 off of that extended decimal, divide by 5, and we get 6.76. What that means right now, the fact that that rate of change is positive, means that this is growing, it's increasing. And as I said, if they've given us units, that maybe this is 6.76 people per day, we know what's happening. And we could compare it, what happens in days 0 through 5, to what happens in days 10 through 15. Is the population getting better? Like, is it growing even more or not? And so here, if we look at the average rate of change, P15 minus P10 over 15 minus 10, that's dividing by 5. This time I just plugged it all in because you're getting decimals on both of them, and I don't want to have to write something down and round it off and then write down the next one. So I just plugged in the whole thing, first of all with a D of 15, then a D of 10, hit equals, and got 60.57 with a whole bunch more decimal places, and rounding, so dividing that, we're getting 12.11. So if we had units on this, and for example, maybe this was people per day, that means over the 10th to 15th day, the population is growing faster. We're getting 12 people per day as opposed to 6 people per day, or almost 7 people per day. So once this gets into applications, you can use it to interpret what's happening. For now, though, just getting comfortable with that formula, and it is slope. Don't make it any harder than that. This is a slope formula. It's just with the function notation, sometimes that causes some stress. And remember that it's an average rate of change. We're approximating what's happening on that curve by choosing 2 points to create a secant. If we choose 2 points around a turning point, it's not a very useful average rate of change. You can still do it, but it doesn't mean much. So I think they have some in here with pictures as well, and just try and kind of interpret what the answer means and how it connects to what you know about slope, now called rate of change. And I think that's it.